Welcome to the Explainer. We're getting pretty used to AI doing some incredible things, but there's this one huge question that keeps coming up. How do we actually know what's going on inside its head? How can we understand what it's really thinking?
Okay, so take a look at this picture. Right away, you and I know exactly what we're looking at. It's a red panda, right? And if someone asked us why, we could tell them. We'd point out the reddish-brown fur, that super bushy tail, the little white face with whiskers. Simple. But what about an AI? When it gets the answer right, how? That's where we start to enter this really fascinating and kind of murky territory.
So how does an AI know? It seems like it should be a straightforward question, but the answer is anything but. We feed these things millions and millions of images. And yeah, they learn to spot patterns. But the actual how, the specific logic it builds for itself, is often a total mystery, even to the people who designed it.
And this right here is what the experts call the black box problem. Think about it. You put your data in one end, a perfect answer pops out the other. But what happens in between? It's a complete unknown. We can't see the thought process, we can't see the reasoning. And that's a huge problem, right? Because how can you trust something if you don't know why it's making its decisions? Especially when we're talking about really high-stakes stuff like in medicine or finance.
Okay, so this is where things get really cool. Because researchers weren't just going to sit back and accept this black box forever. They've been trying to figure out a way to basically force the AI to show its homework, to make it lay out its thinking process in a way that we humans can actually understand and follow.
And the solution they came up with is called a Concept Bottleneck Model. The name sounds a little technical, but the idea behind it is just brilliant. It's so clever. Instead of letting the AI jump straight from the image to the answer red panda, it has to pass through this middle step, this bottleneck. And at that bottleneck, it is forced to first identify a list of concepts that make sense to us. It has to check off boxes like has reddish-brown fur, has a long shaggy tail, and has pointy ears.
So what does this do? It essentially turns that black box into a glass box. We can actually look inside and see its reasoning. We can follow the logic. If the model says, yep, this is a red panda because I saw wings and feathers, we know immediately that something's gone haywire. It makes the whole process transparent, and that's the first big step toward building trust.
Now this sounds amazing, but there was one massive problem, a huge roadblock. Think about it, creating those concept checklists for every single object you want an AI to recognize, birds, cars, plants, thousands of them. It would take an insane amount of human work. The idea was great, but it just wasn't practical at a large scale. That is, until a new approach came along that completely changed the game by bringing in a whole different kind of AI, a language model.
So to get around that scaling problem, researchers came up with this model called Labo. And the secret sauce here is that it uses a large language model, an LLM. You've definitely heard of these. It's the same kind of tech that powers things like ChatGPT. Basically, an AI that's an expert in human language. What Labo does is it uses the LLM to do the heavy lifting, to automatically generate that whole list of concepts for it. And the way it works is actually pretty straightforward. Let me break it down. First, Labo basically just asks the LLM a simple question, like, hey, describe a red panda for me. The LLM spits out a bunch of descriptions. Then, step 2, Labo's own algorithm sifts through all that text and picks out the most useful, the most defining concepts. Step 3, it looks at the actual image and gives a score for each concept, like how much bushy tail is in this picture. And then finally, it puts all those scores together to make its final call, yep, that's a red panda. And get this is the really wild part. You might think that by forcing the AI to go through this extra step, you'd lose some accuracy. But look at the data. This glass box model, Labo, isn't just more understandable, it's actually more accurate than the standard black box model. I mean, that's the holy grail, right? You get better explanations and you get better results. It's a total win-win. So, problem solved, right? It sounds perfect. We've got amazing accuracy. We can see exactly how the AI is thinking. It really feels like this is it. We've cracked the code for making AI we can finally trust. But, in science, just when you think you've got it all figured out, that's usually when the story takes an unexpected turn. And that's exactly what happened here, because a whole new, much trickier question started to pop up. Okay, the AI is giving us an explanation, but how do we know it's the real explanation? How can we be sure that's the logic it actually used to make its decision, and not just something it cooked up afterwards?
Yeah, check out this quote from another paper on the topic. It really nails the problem. What researchers started to find was that these models are really good at giving us explanations that look good,
They're compelling, they make sense to us, but, and this is a huge but, they're not always faithful to what's actually happening under the hood.
And that's the absolute key distinction we need to wrap our heads around. A compelling explanation tells a good story, but a faithful explanation tells the true story. So the AI might say, I identified this panda because of its furry texture, because it knows that sounds like a good reason to a human. But what if it actually focused on some random weird pixel pattern in the background and it just made up the furry texture part because it knew that's what we wanted to hear?
Let's make this super concrete. Look at these two. On the left, an oxalotl. On the right, a tree frog. Now, a truly faithful explanation for identifying the oxalotl would have to involve a super specific feature, right? Like those little feathery things on its head, the external gills. If the AI just said, oh, I knew it was an oxalotl because it's found near water, well, that's compelling, but it's not very helpful, is it? Because the frog is also found near water. It's not a faithful explanation of what makes them different.
And this brings us right up to the present day, to the absolute cutting edge of AI research. The goalposts have shifted. It's not enough anymore to just get an explanation out of an AI. The new challenge, the next frontier, is about proving that the explanation is actually true. The quest is for what they call provable faithfulness.
So let's just recap where we are on this whole quest. We started out trying to crack open that black box, right? And we did. We found these incredible tools like Concept Bottleneck Models, supercharged by language AI that let us peek inside. But by opening that box, we found another, even harder problem inside. We learned that just because an AI can talk like a human and give us reasons, it doesn't mean it's being honest about its own thought process. So the whole focus of the field has moved from just getting an explanation to demanding actual proof.
Which leaves us with this one big final question to think about. For the longest time, I think we all just assumed that if we could understand an AI, we could trust it. But what if those are two completely different things? What if sometimes they're even in conflict? As AI gets woven into every part of our world, figuring out that tension, the balance between an answer we can understand and an answer we can truly, genuinely trust, that is going to be the challenge for the next generation of AI.